Chapter 5 Periodic Classification of Elements. Early attempts to classify elements. Need for classification. Let us have a look at how things are arranged at various places, such as in a shopping mall or in your school library. Is there a particular pattern in which things are arranged? Yes, they are arranged as per their category. In a shopping mall, toiletries are kept on separate shelves. Utensils are kept on different racks. Food items are kept in a different section. In your school library also, books are arranged as per their category. Books on various subjects, dictionaries, encyclopedias and storybooks are grouped on separate shelves. Even at home, your mother often asks you to arrange your textbooks, notebooks, stationery items, clothes and other accessories in separate drawers. Why are things arranged in a certain way? This is because when things are arranged properly as per their category, it is easy to locate them or retrieve them whenever required. In the same way, elements are classified in a systematic way to study their properties. But this classification did not happen in one day. Many scientists made several attempts to develop the present system of classification. Earlier methods of classification of elements. Earlier, on the basis of their properties, elements were classified as metals and non-metals. But this method of classification was not very successful, as there were some elements which showed properties of both metals and non-metals. They could not be placed in any of the two groups. After several studies, scientists came to the conclusion that the atomic mass can be considered as the basis for classifying elements. Dobereiner was one of the early scientists who attempted to classify elements on the basis of their atomic masses. Dobereiner's triads. Johann Wolfgang Dobereiner was a German scientist who studied pharmacy at Münchberg in Germany and then chemistry at Strasbourg. Later, he became a professor of chemistry and pharmacy at the University of Jena. During his study in the year 1829, he came across several groups of three elements or triads which showed similarities in properties. These triads were called Dobereiner's triads. Dobereiner found that in a triad, the atomic mass of the middle element was approximately equal to the mean of the atomic masses of the other two elements. Let us consider some such triads. Lithium, sodium and potassium form a triad. The atomic mass of lithium is 6.9 and that of potassium is 39. The mean of their atomic masses is 23. Which is the atomic mass of sodium. Calcium, strontium and barium also form a triad. The atomic mass of calcium is 40.1 and that of barium is 137.3. The mean of their values is 88.7. This value is approximately equal to the atomic mass of strontium, which is 87.6. Chlorine, bromine and iodine form a triad. The atomic mass of chlorine is 35.5 and that of iodine is 126.9. The mean of these values is 81.2, which is approximately equal to the atomic mass of bromine, which is 79.9. Sulfur, selenium and tellurium also form a triad. The atomic mass of sulfur is 32 and that of tellurium is 128. The mean of these values is 80, which is approximately equal to the atomic mass of selenium, which is 79. However, this method of classification of elements was not very successful because all the elements known at that time could not be arranged in the form of triads. Newlands Law of Octaves. After the failure of Dobereiner's triads, Newlands tried to classify elements in the increasing order of their atomic masses and came up with his periodic table. This periodic table was based on the law of octaves. Newlands was an English chemist born in London. He studied at the Royal College of Chemistry. He arranged the 56 elements then known in the increasing order of their atomic masses. He divided the elements into horizontal rows of 7 elements each. This was called as Newlands' periodic table. He found that every 8th element had properties similar to that of the first. This trend was similar to the octaves of music, where the 8th note is similar to the first. Newlands proposed a law of octaves which states that when elements are arranged in the increasing order of their atomic masses, the properties of the 8th element are similar to the first. Therefore, his classification was known as Newlands' octaves. However, Newlands' octaves failed because of some drawbacks. Only elements like lithium, sodium and potassium, beryllium, magnesium and calcium, and pairs of elements like boron and aluminium, carbon and silicon, nitrogen and phosphorus, oxygen and sulfur, and fluorine and chlorine showed similarities in properties. Every 8th element after calcium did not show properties similar to the first one. Another drawback was that, as more and more elements were discovered, they could not be fitted into Newlands' periodic table. In certain places of the periodic table, he adjusted 2 elements which differed in properties in the same position. This was done to accommodate the existing elements. But this arrangement was not according to the law of octaves. Newlands also could not include inert gases in the table because they were not discovered. The first successful classification, Mendeleev's periodic table. Dmitri Mendeleev, a Russian chemist, had great interest in the study of elements. Mendeleev studied the relationship between the atomic masses of elements and their physical and chemical properties. He concentrated on the compounds formed by the elements with oxygen and hydrogen as they were very reactive and formed compounds with most of the elements. He analyzed these compounds and came to the conclusion that the atomic mass of elements was the most fundamental property for classifying elements. Mendeleev arranged elements in the order of their increasing atomic masses and observed that elements having similar physical and chemical properties occur at regular intervals or occur periodically. This observation was stated in the periodic law known as Mendeleev's periodic law. The law states that the physical and chemical properties of elements are a periodic function of their atomic masses. Mendeleev arranged the 63 elements then known according to their properties in horizontal rows till he came across an element which had properties similar to the first element. He placed this element below the first element and thus started the next row of elements. This arrangement is called the Mendeleev's periodic table. Salient features of Mendeleev's periodic table. In Mendeleev's periodic table, the horizontal rows are called periods. There are 7 periods and they are numbered from 1 to 7. as one moves from left to right in a period, there is a gradual change from metallic to non-metallic properties. There are 8 vertical columns called groups. They are numbered from 1 to 8. Groups 1 to 7 are further divided into 2 subgroups A and B. Mendeleev's periodic table was the first successful classification of elements. It had both merits and demerits. Let us see both the merits and demerits of Mendeleev's periodic table. Achievements of Mendeleev's periodic table. In Mendeleev's periodic table, he left some blank spaces. These vacant spaces were left for including elements that were not discovered at that time. Mendeleev could also predict the properties of these unknown elements on the basis of the properties of the elements lying adjacent to these vacant spaces. He predicted the presence of 3 elements. They were named as Eka boron, Eka aluminium, and Eka silicon. The properties of these 3 elements were similar to the actual elements discovered later. Eka boron was similar to scandium, Eka aluminium was similar to gallium, and Eka silicon was similar to germanium. Let us compare the properties of the predicted element Eka aluminium Ea and the element gallium Ga, which was discovered later. The atomic weight of Eka aluminium was about 68 and that of gallium is 69.72. The density of Eka aluminium was approximately 5.9 grams per cubic centimeter and that of gallium is about 5.94 grams per cubic centimeters. The melting point of Eka aluminium was predicted to be low and that of gallium is also quite low, that is 30.2 degrees Celsius. The valencies of Eka aluminium and gallium are the same, that is 3. The formula of the oxides of both these elements is similar. Eka aluminium oxide is Ea2O3 and gallium oxide is Ga2O3. The formula of the chlorides of both these elements is also similar. Eka aluminium chloride is EaCl3 and gallium chloride is GaCl3. Demerits of Mendeleev's periodic table. Hydrogen showed properties similar to alkali metals and halogens. Therefore, in the periodic table, hydrogen was not given a fixed position. Let us explore if there is any resemblance between hydrogen and alkali metals by writing compounds of both with chlorine, sulfur and oxygen. The compound of hydrogen with chlorine is hydrogen chloride, HCl. Compound with sulfur is hydrogen sulfide, H2S. And compound with oxygen is water, H2O. Consider the compounds of an alkali metal, sodium. The compound of sodium with chlorine is sodium chloride, NaCl. Compound with sulfur is sodium sulfide, Na2S. And compound with oxygen is sodium oxide, Na2O. You can see that the formulae of the compounds formed by hydrogen and those with sodium are similar, as both hydrogen and sodium have valency 1. Let us now discuss the similarity between hydrogen and halogens. Both hydrogen and halogens exist as diatomic molecules. Hydrogen exists as H2 and chlorine, which is a halogen, exists as Cl2. Hydrogen forms covalent compounds like methane and chlorine also forms covalent compounds like carbon tetrachloride. Another demerit was that isotopes of the same element were given the same position in the periodic table. For example, isotopes of oxygen were given the same position as they are chemically similar. But, according to Mendeleev's law, isotopes of the same element should be given different positions because they have different atomic masses. It was observed that at certain places in the periodic table, an element with a higher atomic mass like cobalt, with atomic mass 58.93, was placed before an element with lower atomic mass, that is, nickel with atomic mass 58.71. Certain chemically dissimilar elements were placed together. Manganese was placed with halogens, though they both are chemically dissimilar. Henry Moseley tried to correct these defects in the modern periodic table, which is the present system of classification of elements. Moseley and the modern periodic table. In 1913, Henry Moseley, an English physicist, discovered that the fundamental property of an element was the atomic number and not atomic mass. He therefore considered the atomic number as the basis for classifying elements. He realized that if elements are arranged in the order of increasing atomic numbers, elements with similar properties are repeated after regular intervals. Moseley modified Mendeleev's periodic law and formulated the modern periodic law. The modern periodic law states that the chemical and physical properties of elements are a periodic function of their atomic numbers. Based on this law, the modern periodic table came into existence. The modern periodic table is also called as the long form of periodic table. Position of elements in the modern periodic table. The modern periodic table contains 7 horizontal rows called periods and 18 vertical columns called groups. Apart from the 7 rows, there are 2 additional rows placed separately at the bottom of the table. The entire table is divided into 4 blocks: S block, P block, D block, and F block. Periods in the modern periodic table. The 7 periods in this periodic table are numbered from 1 to 7. Elements present in the same period have the same number of shells, and the period number is equal to the number of shells. For example, the elements belonging to the first period will have 1 shell, that is only the K shell. The elements belonging to the second period will have 2 shells, that is the K shell and the L shell. The elements belonging to the third period will have 3 shells, K shell, L shell, and the M shell. The number of elements present in each period is equal to the maximum number of electrons present in the outermost shell. This rule is applicable only to the first 3 periods. You know that the number of electrons present in each shell is given by the formula 2n squared, where n is the shell number. K shell is the first shell, so the value of n is 1 and the number of electrons is 2. Therefore, the first period will contain 2 elements. L shell is the second shell, so the value of n is 2 and the number of electrons is 8. Therefore, the second period will contain 8 elements. M shell is the third shell, so the value of n is 3 and the number of electrons is 18. But since the outermost shell can have 8 electrons, the third period contains 8 elements. Periods are classified into different types according to the number of elements present. The first period has only 2 elements. It is the shortest period. The second and third period have 8 elements each. They are short periods. The fourth and fifth periods have 18 elements each. They are long periods. The sixth period is the longest period, containing 32 elements. The seventh period is an incomplete period. It has a capacity to accommodate 32 elements, many of which have been discovered. Now, let us write the electronic configuration of the elements from atomic number 11 to 18 belonging to the third period. The first element is sodium, Na. The electronic configuration is 2, 8, 1. Magnesium, Mg. Electronic configuration 2, 8, 2. Aluminium, Al. Electronic configuration 2, 8, 3. Silicon, Si. Electronic configuration 2, 8, 4. Phosphorus, P. Electronic configuration 2, 8, 5. Sulfur, S. Electronic configuration 2, 8, 6. Chlorine, Cl. Electronic configuration 2, 8, 7. Argon, Ar. Electronic configuration 2, 8, 8. You can observe that all these elements have the same number of electrons in the K shell and the L shell, but the number of valence electrons increases along the period. Sodium has 1 valence electron, magnesium has 2, aluminium has 3, silicon 4, phosphorus 5, sulfur 6, chlorine 7, and argon has a complete octet. Groups in the modern periodic table. There are 18 groups in the modern periodic table. They are numbered from 1 to 18. Group 1 contains alkali metals. Group 2 contains alkaline earth metals. Group 17 contains halogens, and Group 18 contains noble gases. All the elements in a group have the same number of electrons in their outer shell. That is why elements of a particular group have similar chemical properties. Do all these elements have the same number of valence electrons? No, they do not. This is due to the fact that the elements belonging to group 1 have 1 electron in the outermost shell, that is, 1 valence electron. Similarly, the elements belonging to group 2 have 2 valence electrons. Elements belonging to group 13 have 3 valence electrons, and the elements belonging to group 17 have 7 valence electrons. Electronic configuration and the types of elements. On the basis of the electronic configuration of elements, the periodic table is also divided into 4 blocks: the S block, P block, D block, and F block. Elements in group 1 and 2, together with hydrogen, form the S block elements. They have 1 or 2 electrons in their last shell. All these elements except hydrogen are metals. Potassium K is a group 1 element with atomic number 19. Its electronic configuration is 2881. Magnesium Mg is a group 2 element with atomic number 12. Its electronic configuration is 282. Both these elements are S block elements. Elements in group 13 to 17 and group 18 or group 0 form the p block elements. They have 3 to 8 electrons in their outermost shell. Elements in this block may be metals, non-metals, or metalloids. Metalloids are elements which show properties of both metals and non-metals. For example, chlorine, a group 17 element with electronic configuration 2,7, is a p block element. Elements present in group 18 are also called as noble gases. For example, argon, a group 18 element with electronic configuration 288, is a noble gas. These elements have completely filled outermost shells. Elements in group 3 to group 12 are called d block elements. They have their last two shells incompletely filled. All these elements are metals. The elements placed at the bottom of the periodic table are the F block elements. They contain two series of elements called lanthanides and actinides. Lanthanides contain 14 elements starting with cerium Ce with atomic number 58 to lutetium Lu atomic number 71. Since all these elements have properties similar to those of lanthanum La with atomic number 57, they all are placed along with lanthanum in group 3 and period 6. Actinides contain 14 elements starting with thorium Th with atomic number 90 to lawrencium Lr atomic number 103. Since all these elements have properties similar to those of actinium Ac with atomic number 89, they all are placed along with actinium in group 3 and period 7. The lanthanides and actinides together form the F block elements. They have their last 3 shells incompletely filled. All these elements are metals. The elements of the S and P block elements together, except the group 18 elements, are normal elements. The elements in group 18 or group 0 are called inert elements or noble elements. The D block elements are transition elements. The F block elements are called inner transition elements. The classification of elements in the modern periodic table was helpful in explaining the anomalies in Mendeleev's classification. Merits of modern periodic table over Mendeleev's periodic table. Many demerits of Mendeleev's periodic table, like the position of hydrogen and isotopes, were cleared in Moseley's periodic table. The atomic number of hydrogen is 1. Therefore, hydrogen should be placed at the extreme left-hand side of the periodic table above alkali metals because its electronic configuration is similar to alkali metals, but many of its properties are different from those of alkali metals. Hence, while discussing alkali metals, hydrogen is not included. Isotopes of elements have different atomic masses, but they have the same atomic number. That is why they are placed at the same position in the modern periodic table. The atomic number of cobalt is 27 and that of nickel is 28. Hence, cobalt is placed before nickel in the periodic table, although its atomic mass is greater than nickel. The main feature of the modern periodic table is that the position of an element in the periodic table is related to the electronic configuration of that element. It has been observed that properties reappear at regular intervals in the periodic table due to similar electronic configurations. Such properties, which show a gradual variation in a group or a period and they repeat themselves after regular intervals of atomic number are called periodic properties. This happens because elements in a group have the same number of valence electrons and elements in a period show an increase in the number of valence electrons. Valency, atomic size, and metallic and non-metallic properties are periodic properties. Trends in the modern periodic table. Valency. The valency of an element is determined by the number of valence electrons present in the outermost shell of an atom. How does the valency vary in a group? Let us consider some elements of group 1, group 2, group 14, group 17 and group 18 or group 0 to understand this. Lithium and sodium belong to group 1 of the periodic table. The electronic configuration of lithium is 2-1, that of sodium is 2-8-1. Since there is only one electron in the outermost shell of these two elements, the valency of these elements is 1. Magnesium and calcium belong to group 2 of the periodic table. The atomic number of magnesium is 12, with electronic configuration 2-8-2. The atomic number of calcium is 20, with electronic configuration 2-8-8-2. Since there are 2 electrons in the outermost shell of these two elements, the valency of both these elements is 2. Carbon and silicon belong to group 14 of the periodic table. The atomic number of carbon is 6, with electronic configuration 2-4. The atomic number of silicon is 14, with electronic configuration 2-8-4. Since there are 4 electrons in the outermost shell of these two elements, the valency of both these elements is 4. Fluorine and chlorine belong to group 17 of the periodic table. The atomic number of fluorine is 9, with electronic configuration 2-7. The atomic number of chlorine is 17, with electronic configuration 2-8-7. Since these elements require only one electron to complete their octet, the valency of both these elements is 1. Helium and neon belong to group 18 or group 0 of the periodic table. The atomic number of helium is 2. Therefore, its electronic configuration is also 2. The atomic number of neon is 10, with electronic configuration 2-8. Both are inert gases. Helium has a complete duplet state, while neon has a complete octet state. Therefore, the valency of both these elements is 0. From these examples, we can say that all the elements in a group have the same number of valence electrons. That is, the valency of all the elements in a given group is the same. And the molecular formulae of the compounds formed are also the same. For example, the chlorides of alkali metals have the formula LiCl, NaCl, KCl, and so on. How does the valency vary in a period? The valency varies gradually from left to right along a period depending upon the varying electronic configuration. We may consider some elements of the second period and third period to understand this. In the second period, the valency of lithium is 1, beryllium is 2, boron is 3, carbon is 4, nitrogen is 3, oxygen is 2, fluorine is 1, and neon is 0. In the third period, the valency of sodium is 1, magnesium is 2, aluminium is 3, silicon is 4, phosphorus is 3, sulfur is 2, chlorine is 1, and argon is 0. Therefore, we can say that in the second and the third period, the valency increases from 1 to 4 and then decreases from 4 to 0 as we go from left to right in a period. Atomic size. Atomic size is the next periodic property. Atomic size is determined using the atomic radius. The atomic radius for an isolated atom is the distance from the center of the atom to the outermost shell. Consider the atomic radius of the first 4 elements of group 17. The atomic radius of fluorine is 72 picometer, chlorine is 99 picometer, bromine is 114 picometer, and iodine is 133 picometer. This shows that the atomic size increases from fluorine to iodine in the group. As we move from fluorine to iodine in the group, the number of shells increases. Consequently, the electrons are added to the new shells. Since the outermost electrons are farther from the nucleus, therefore they do not experience a greater pull from the nucleus. This causes an increase in the atomic size. We may conclude that as we move down a group, the atomic size increases. Now, let us consider the atomic radius of the elements of third period. The atomic radius of sodium is 190 picometer, magnesium 160 picometer, aluminium 143 picometer, silicon 132 picometer, phosphorus 128 picometer, sulfur 127 picometer, chlorine 99 picometer, and argon is 71 picometer. This indicates that the atomic size decreases from sodium to argon across the period. All these elements have the same number of shells in their atoms, so electrons are added to the same shell. These electrons, therefore, experience a greater pull from the nucleus. This causes a decrease in the atomic size. Thus, as we move across a period, the atomic size decreases. The next periodic property is the variation in metallic and non-metallic properties in a group and in a period. Metallic and non-metallic properties. Most metals have a small number of electrons, that is up to 3 in their outermost shell. They show a tendency to lose electrons and therefore are said to have electropositive character. Non-metals have 4 or more electrons in their outermost shell. Hence, they show a tendency to accept electrons. Thus, they are said to have electronegative character. Non-metals also show a tendency to share electrons with other atoms. We know that in a period the atomic size decreases, therefore the tendency of atoms to lose electrons also decreases across a period. In other words, the metallic character decreases and the non-metallic character increases across a period. That is why the elements on the left-hand side of a period are metals and those on the right-hand side are non-metals. In a group, the atomic size increases, hence the tendency of atoms to lose valence electrons also increases down a group. Thus, as we move down a group, the metallic character increases. Let us consider the elements of group 14. The first element is carbon, symbol C, which is a non-metal, then silicon, symbol Si, and germanium, symbol Ge, which are the 2 metalloids, and the remaining elements, tin, symbol Sn, and lead, symbol Pb, which are metals. Metalloids show properties of both metals and non-metals. Thus, in this group, there is a decrease in non-metallic character and increase in metallic character from carbon to lead. In the modern periodic table, there is a zigzag line that separates the metals from the non-metals. The elements on the border line are metalloids or semi-metals like boron, symbol B, silicon, symbol Si, germanium, Ge, arsenic, As, tellurium, Te, and polonium, Po.